Imagine standing on the edge of a cliff. Below you, there's nothing. Just darkness. You can't see the bottom. You don't know what's down there. Now imagine that cliff is real, and it drops not a few hundred feet, but nearly 7 miles straight down into blackness so complete that no sunlight has ever touched it. That's the ocean floor. And for most of human history, we assumed it was empty. Barren. A dead zone. A wasteland of pressure and cold and silence where nothing could possibly survive. We were wrong. Not just a little wrong. Catastrophically, embarrassingly, completely wrong. Because what scientists have been discovering over the last 50 years, slowly, quietly, with very little fanfare, is that the bottom of the ocean is one of the most complex, most active, and most densely populated environments on the entire planet. There are mountain ranges down there longer than the Himalayas. There are volcanoes that have been erupting continuously for thousands of years. There are rivers, actual rivers, flowing along the ocean floor with their own banks and their own currents. And there are structures, towering, ancient, intricate structures, that look for all the world like cities. Not cities built by humans, but cities nonetheless. This is the story of what lives at the bottom of the world. The ocean covers about 71% of the Earth's surface. That's a number most people have heard before, but it rarely sinks in what it actually means. It means that the majority of our planet, the majority, is underwater. And of that vast underwater world, humans have explored less than 20%. Some estimates put the number closer to 5%. Think about that for a moment. We have better maps of the surface of Mars than we do of our own ocean floor. We have sent probes to the outer edges of the solar system. We have landed rovers on another planet. We have pointed telescopes at galaxies billions of light years away. And yet the bottom of the sea, right here on our own planet, remains almost entirely unknown to us. The reason is simple, and it's the same reason those depths are so mysterious: pressure. For every 10 meters you descend into the ocean, the pressure increases by 1 atmosphere. At the surface, the pressure is 1 atmosphere, the weight of the air above you. At a depth of 100 meters, it's 11 atmospheres. At 1,000 meters, it's 100 atmospheres. At the very bottom of the Mariana Trench, the deepest point in any ocean, the pressure is over 1,000 times greater than what you feel standing on the beach. That kind of pressure doesn't just crush submarines. It crushes ideas. It crushes curiosity. Because for centuries, the assumption was that nothing could survive under those conditions. And then we started looking. The first real glimpse of the deep ocean came in 1960, when 2 men climbed into a vessel called the Trieste and descended to the bottom of the Mariana Trench. Their names were Don Walsh and Jacques Picard. The journey took nearly 5 hours. When they finally touched down on the seafloor, nearly 11 kilometers below the surface, they expected to find nothing. Instead, they found a flatfish. Just sitting there. On the floor of the deepest place on Earth. A fish, calmly existing in conditions that should have made life impossible. Walsh later said it was one of the most shocking moments of his life. Because everything they thought they knew about the limits of biology, about where life could and could not exist, was wrong in that instant. But that was just the beginning. The real discoveries came 17 years later, in 1977, when a team of oceanographers aboard a research vessel called the Nor was surveying the seafloor near the Galapagos Islands. They were looking for hydrothermal vents, cracks in the ocean floor where heat from the Earth's interior escapes into the water. They expected to find some interesting geology. What they found instead rewrote the rules of life on Earth. The vents were real. And they were spectacular. Columns of superheated water, sometimes reaching temperatures of over 400 degrees Celsius, shooting up from the seafloor like chimneys. But surrounding those chimneys, clustered around them in dense communities that shouldn't have existed, were animals. Enormous tube worms, some of them over 2 meters long. Giant clams. shrimp, crabs, mussels. All of them living in complete darkness, under crushing pressure, in water that would boil a human alive, and thriving. How? The answer was so unexpected that it took scientists years to fully accept it. These animals weren't living off sunlight. They were living off the earth itself. The bacteria at the base of the food chain in these communities didn't photosynthesize. They chemosynthesized, using the chemicals pouring out of the vents as their energy source. Hydrogen sulfide, methane, carbon dioxide, substances toxic to most life on Earth, were, for these organisms, food. It was the first ecosystem ever discovered that had no connection whatsoever to the sun. And it changed everything. Because if life doesn't need sunlight to survive, then life can exist anywhere there's chemical energy and water. That means life might exist in the oceans beneath the ice of Europa, one of Jupiter's moons. It means life might exist deep within the crust of Mars. It means the universe, which we had assumed was almost entirely lifeless, might in fact be teeming with organisms we never imagined. But we're getting ahead of ourselves. Because back here on Earth, the discoveries were just getting started. Over the following decades, as submarine technology improved and deep-sea exploration became more systematic, the picture that emerged from the ocean floor grew more and more extraordinary. The hydrothermal vents at the Galapagos were not unique. They were everywhere. Thousands of them, scattered along the mid-ocean ridges, the vast underwater mountain ranges that circle the globe like the seams on a baseball. And each vent was its own world. Each one had its own unique community of organisms, often found nowhere else on Earth. Species that had evolved in complete isolation, adapted to the specific chemistry of that particular vent, that particular temperature, that particular depth. Scientists began to realize that the deep ocean wasn't a barren wasteland. It was a mosaic of microhabitats, each one a unique ecosystem, each one potentially harboring species that science had never seen. The numbers became staggering. It's estimated that the deep ocean contains somewhere between 500,000 and 10 million species that have never been described. Some researchers think the number is higher. Every time a new expedition goes down, it comes back with creatures that don't fit into any existing category. Things with no eyes, things with hundreds of eyes, things that glow in the dark, things that produce their own light, things that live inside rocks, things that eat rocks, things that have been sitting on the seafloor for so long that they're covered in hundreds of years of sediment and still alive. But the animals, as extraordinary as they are not the most visually stunning thing about the deep ocean. That would be the structures. In 2000, a team of researchers discovered a hydrothermal vent field in the Atlantic Ocean that they named the Lost City. Unlike the black smoker vents found at the Galapagos and other mid-ocean ridges, the Lost City vents were white. Towering white columns of carbonate minerals, some of them 60 meters tall, rising from the seafloor like the pillars of an ancient temple. The tallest structure, which the researchers named Poseidon, stands 18 stories high and has been growing for at least 30,000 years. 30,000 years. When Poseidon began forming, humans were still hunter-gatherers. The pyramids of Egypt were 25,000 years in the future. The Roman Empire wouldn't exist for another 29,000 years. And this structure, this white tower rising from the floor of the Atlantic Ocean, was already there, already growing, already creating its own ecosystem of microbes and chemistry that operates by rules completely unlike anything on the surface. The Lost City is not unique either. Similar structures have since been found in other ocean basins. And each time they're discovered, the same reaction occurs among the scientists who see them for the first time, a kind of stunned silence, followed by the same word. City. Not because they were built by intelligent beings, but because of the scale, the complexity, the density of life. The sense that you are looking at something that has its own logic, its own organization, its own ancient history that dwarfs anything humans have ever built. Then there are the cold seeps. Cold seeps are areas of the seafloor where hydrogen sulfide, methane, and other hydrocarbon-rich fluids seep slowly up through the sediment. Unlike hydrothermal vents, they don't produce dramatic columns of superheated water. They're quieter, more subtle. But what they produce is equally extraordinary. Around cold seeps, researchers have found communities of organisms so dense, so complex, so ancient that the word community barely does them justice. There are tube worms at cold seeps in the Gulf of Mexico that are estimated to be over 250 years old, older than the United States. There are clam beds that have been continuously inhabited for thousands of years. There are microbial mats, vast, flat, carpet-like growths of bacteria that cover acres of seafloor and produce chemicals that no surface organism has ever encountered. And perhaps most remarkably, there are brine pools. A brine pool is exactly what it sounds like, a pool of extremely salty water sitting on the ocean floor. Because the brine is so much denser than the surrounding seawater, it doesn't mix. It just sits there, in a depression on the seafloor, with a distinct surface and even small waves. Underwater lakes. On the bottom of the ocean. When submersibles first encountered these pools, the reaction of the scientists inside was, by their own accounts, one of complete disorientation. They were underwater, looking at what appeared to be a shoreline, a beach, a body of water with a visible surface and gentle waves. Except they were already underwater. It violated every intuitive sense of what underwater means. Some of these brine pools are called the jacuzzi of despair by researchers, because any animal that falls into them is instantly killed by the hypersaline, oxygen-depleted water. The edges of the pools are littered with the bodies of crabs and fish that wandered too close. And yet, even here, even in a pool of water so toxic it kills almost everything that touches it, life finds a way. Certain microbes thrive in the brine itself, living in conditions that would be lethal to virtually every other organism on Earth. The deep ocean also has mountains. Not small ones. The mid-ocean ridge system is the longest mountain range on Earth. It stretches over 65,000 kilometers, more than 1.5 times around the entire planet. Most of it is completely underwater, completely unexplored, and almost entirely unknown to the general public. The tallest peaks of the mid-ocean ridge rise nearly 3 kilometers above the surrounding seafloor, comparable to many mountains on land, but hidden beneath miles of water. Along the ridges, the ocean floor is constantly being created. Magma from the Earth's mantle wells up through cracks, cools into new rock, and pushes the existing seafloor outward in both directions. This is the process that drives plate tectonics, the slow, grinding movement of the continents that has been reshaping the face of the Earth for billions of years. The ocean floor is not static. It's alive with geological activity, constantly renewing itself, constantly creating new habitat for the organisms that have learned to live there. And where the ocean floor is being destroyed, where one tectonic plate slides beneath another at a subduction zone, there are the deepest places on Earth. The Mariana Trench, where Walsh and P. Carr made their historic descent, is the deepest of these, but it's far from the only one. The Tonga Trench, the Philippine Trench, the Kuril-Kamchatka Trench, all of them plunging to depths that make Everest look modest, all of them harboring life in forms we are only beginning to understand. There's a creature called the barreleye fish that lives in the deep ocean at depths between 400 and 2,000 meters. It's translucent. You can see through its head. Its eyes, two brilliant green tubes pointing upward through its transparent skull, are designed to detect the faint silhouettes of creatures swimming above it against the distant glow of sunlight filtering down from the surface. It can rotate those eyes forward to focus on prey directly in front of it. It lives in a world of permanent twilight, using light that has traveled thousands of feet through water to hunt creatures it can barely see. There is a fish called the anglerfish, famous enough to have appeared in animated movies, that uses a bioluminescent lure dangling from its head to attract prey in the absolute darkness of the deep ocean. The female anglerfish is the one with the lure. The male is dramatically smaller, often less than a centimeter long compared to the female's 40 centimeters. When the male finds a female, he bites into her body and fuses with her permanently. His circulatory system merges with hers. His eyes and internal organs degenerate. He becomes, functionally, a reproductive appendage, a parasite that provides sperm in exchange for nutrients from his host's bloodstream. Multiple males can fuse with a single female at the same time. There is a shrimp at hydrothermal vents in the Indian Ocean that has no eyes. Not vestigial eyes, not reduced eyes, but no eyes whatsoever. In their place, it has a strip of light-sensitive tissue along its back that can detect the faint infrared radiation emitted by the vent itself. It doesn't see in any conventional sense. It feels light. It navigates using heat radiation in a world where all other light is absent. These are not edge cases. These are not rare anomalies. The deep ocean is full of creatures like this, organisms so alien, so unlike anything that lives on the surface, that encountering them for the first time feels less like marine biology and more like first contact. And yet, for all of its strangeness, the deep ocean is also fragile. In recent years, as deep-sea mining has become economically viable, as the demand for rare earth minerals used in electric vehicles and smartphones and renewable energy technology has grown, companies have begun looking at the seafloor as a resource to be extracted. The nodule fields of the deep Pacific contain enormous deposits of cobalt, nickel, manganese, and copper, sitting on the seafloor in dense concentrations that would be enormously valuable if they could be brought to the surface. The problem is that the ecosystems living on and around those nodule fields are among the slowest growing and most vulnerable on Earth. The organisms that live there grow at rates measured in millimeters per 1,000 years. A nodule the size of a potato may have taken 10 million years to form. The communities that have built up around these structures, the sea cucumbers, the brittle stars, the microbial mats, exist on a timescale so far beyond human comprehension that the word ancient barely captures it. If those communities are destroyed by mining, and mining would destroy them, they will not recover. Not in a human lifetime. Not in 100 human lifetimes. The damage would be permanent on any timescale that matters to our species. We are on the verge of destroying something we don't understand, for resources we could find elsewhere, in a place we have barely looked. The ocean floor is not empty. It never was. It is one of the most complex systems on Earth, older than the continents, more biologically diverse than the rainforest, more geologically active than anything we can see from the surface. It contains structures that have been growing for 30,000 years, ecosystems that have never touched sunlight, organisms that redefine what life means. And we are only just beginning to understand it. Every expedition that goes down comes back with something that wasn't in the textbooks. Every dive reveals a creature that has never been named, a structure that has never been mapped, a chemistry that has never been analyzed. The ocean floor is, in the truest sense, the last great frontier on Earth, and unlike space, unlike other planets, unlike the inside of a volcano or the surface of the sun, it is somewhere we can actually go.